I'm Jarrod Marshall with Analog Devices. I'm here to talk to you about what our 28 nanometer data converters are enabling for 5G. As wireless macro base stations evolve from 4G to the next generation standard of 5G, they face significant challenges on the transmit and receive end of supporting wider signal bandwidths of up to 800 megahertz. On top of this, the RF signal chain is getting more complex. Carrier frequencies are evolving to sub-6 gigahertz, up to 28 gigahertz and 39 gigahertz in massive MIMO type architectures. The channel capacity demands are ever increasing, and the mediums for propagation are getting more complex at these higher carrier ranges. New spectrum frontiers are emerging, making the receiver challenges that much more complicated. Customers are faced with faster product development cycle times as competition continues to increase, and that requires the need for more flexible system architectures that can quickly pivot to meet end user demand. On top of traditional point-to-point communication or point-to-multipoint communication, 5G will also have multiple application use cases, as we can see, potentially of Internet of Things and of automotive communication buses, unlike seen before. This adds more signal in the spectrum, making it more crowded, putting more additional constraints on data converters in terms of the receive, and also higher bandwidth synthesis demands on the transmit path as well. So there are three pillars to the RF data converters that are enabling 5G systems. Wide bandwidth and high dynamic range are two of the key components. Wide bandwidth front end supports flexible and scalable frequency planning. It simplifies the hardware design by reducing the number of frequency translation stages, relaxing overall filter requirements. The high dynamic range and superior noise performance enables the use of higher order modulation and coding schemes to improve the overall information throughput. Integrated digital signal processing is the second pillar. It enables software-defined platforms by shifting frequency translation, modulation, demodulation, or frequency mixing and filtering designs from the analog domain to the digital domain. This provides customers with a higher level of scalability and flexibility in frequency tuning that cannot be realized in fixed hardware signal chains. The flexibility and scalability allows our customers to adapt and reconfigure their platforms to customize and meet the demands of an ever-changing market needs. Overall, this enables the third pillar, is enabling the transition of systems to more software-defined, from a previously fixed hardware to a more software-defined platform. The combination of the high-performance analog and digital signal processing found in ADI's next-generation 28 nanometer RF data converters are key enablers to enabling the evolution to a new software-defined platform.